Hello. Hello, everyone. So welcome to my session. So today I'm going to talk about our work in ARM processor. So welcome to the world of ARM. So, as a key feature of the ARM Arm64 processors, they support multiple cores. At this moment, we are still leading in this industry. Average in the server area domain, there are usually 64 or 128 cores in a single silicon chip. So that's an advantage for ARM processors. So we have more execute computing unit. And at the same time, vendors are trying to add more hardware accelerators into the same chipset to accelerate specific tasks. So there is a point. So we need to we need to balance between our jobs between the cores, CPU cores, and the specific hardware accelerators. So today I'm going to talk about the work we did so far in this area. So, so people come to say the longer your subject, and then the less attention you get. So I tried hardly to make a shorter one. So I'm going to touch SVE, so which is the ARM vector solution in the server domain, and the hardware accelerators in my session today. So that's a brief introduction of myself. I come from Linaro. Linaro is an organization. We worked on the ARM software ecosystem. So today's content, as I mentioned, we touched a little bit about the software solutions and the hardware accelerator solutions, and the work we did in OpenSSL and JDK. So in this session, if you get to learn something about SVE or hardware accelerators or OpenSSL, okay, I will feel better if that can help you. So why crypto is important? So first thing is, so we get more and more data in the modern days. So, and the second thing is the government, there are a lot of regulations, rules, laws enforced by the government all over the world. I just checked that in Vietnam, we have the government has such laws, and also China, also US, both the government and the industry-wide. So they enforce us to apply encryption on our data. So that's big stuff. So for thinking about every text files, every byte we store in our server, in our disk, you need to do some encryption. And when you want to fetch it, you need to do decryption. So that's a lot of work. The same thing goes for the storage space. We need to compress things. We need to decompress. So to conquer this need, we have two methods, as I mentioned. So we have the CPU processor core method, and we have the specialized hardware method. So, yeah. So let's first check the ARM solutions. So in the software solution, for that, most of the time we are talking about the instructions. So in the ARM world, we have specialized features, specialized instructions, like for SM4, like for AES. So you can find specialized assembly instructions in the ARM ISA, so to processing such type of job. So people are working on that to use the assembly specialized instruction to optimize their libraries. For example, the erasure code or the SM4 encryption library in the OpenSSL. So another software solution is to use the vector instructions, like a single instruction, multiple data. So we have AVX solutions in the x86 world, and in ARM, we have SVE. So SVE stands for Scalable Vector Extension. I will mention it later. So also ARM introduced the matrix extension recently, which is specifically useful for the AI processing. So what is SVE? SVE is vector processing is scalable. That means the register size can be defined by the vendors. So each chipset vendor can pick their proper size for a vector length. They can choose from 128-bit to up to 2048 bit vector length. So, and the beautiful thing for SVE is, so when you as a programmer, software programmer, when you write your code, you don't need to care much about the actual vector length. So either it's 128-bit or it's 512 bits long. So they provide the instruction mechanism to support this, to cover this for you. So in SVE, that's a bit about too much detail. So it has 32 registers, vector registers. As I mentioned, the vector length can vary from 128-bit to 2000 bit maximum. And SVE provide the P register, predicate registers. Predicate registers is like a mask. So we in the vector processing, we define the data as a lens. So the predicate register works like a mask. So you provide the P register, you provide the mask, and then you issue the instruction. So only the lane mark has a proper mark, either 1 or 0. Here is 1. So have a proper mask will be executed. So you don't need to move or cover the this lane somewhere else. You just keep it here, but put a 0 mask in the predicate register, then issue the command, then you get everything done for you. So there is another example, like it's a multiply and plus instruction. So here we can see that we with this mask, the lane 0, 1, 2 will be processed. With 0, 3 is masked. It goes unchanged. So that's quite makes things simpler for programmers. So another important feature for SVE is it's vector length agnostic. That means you, especially in a while loop, you don't need to know the specific architecture chip you are running. Your software has a 128-bit vector length or 256-bit vector length. You just use it's implied by the instruction. For example, here you have the INC instruction. So traditionally in Neon or some other architectures, you have to know that when you increase index, the vector length is 16. That means 16 byte, right? You process in one loop, you only process 16 byte. So, but in SVE world, so whatever, it's if you are running in a 128-bit machine, it increase 16 byte. If you are running on a machine with 256-bit vector length, then it will mean you increase the index by 32, right? When you write down your program, you don't need to care about the actual vector length. That's what it means. Okay, so beyond that, ARM released, really? Okay, I go quick. So ARM extends the SVE to more domain, SVE2, and also the matrix solutions. Okay, with matrix solutions, they introduced the bigger file, register file, so you can process the do some complex stuff like the outer product or two vectors. Okay, so now let's go to the hardware accelerator. So hardware accelerators is another solution. We know that sometimes CPU frequency, their capability goes to a limit. So there is chance that we use specific hardware to do specific computations. Like in Kunpeng 920 chipset, that's the chipset manufactured by the HiSilicon. So inside this chip, there are 4 accelerators working on compression, security, and something more. So we are going to explain the security part. It can do the AES encryption decryption. It can accelerate SM4 encryption decryption as well. So to support that, Linaro worked with HiSilicon, developed the UADK framework. So this is a software framework, but it works for the purpose of this software is to support the hardware accelerators. So it is constructed based on the SMU technology. With SMU, you get the same virtual address between the device and your program, your code. So you just need to give the virtual address to the device, and then it will find it through SMU. Your device can find the proper physical address. Okay, there will be another session today in this room from my colleague. So if you want to learn more details about UADK and the underlying technology, you can come to join his session. So, okay, we mentioned software acceleration, we mentioned hardware acceleration. So now, how can we get the most efficiency, most capability out of it? So that means we need to find some balance. Okay, so we build some balancing strategy. We consider how and in which conditions we put the jobs to which processor, being the software accelerator or the hardware accelerator. We consider the CPU, we consider the memory bandwidths. So when we define the strategy, we need to consider all these criteria. Here in Linaro, we define this solution. It's based on the OpenSSL 3.0. So there are pretty new features comes with the OpenSSL. So OpenSSL 3.0 was released last year, and yeah, the older version, previous version OpenSSL 1 is obsolete so far right now. So the new features here is each application can define their own context. Within the context, it can load their own provider. Provider means execution unit, like an implementation. So you can register different multiple implementations to the same library context. And it also provides a method store. So when the user application want to fetch, that means want to find some processing unit, implementation unit, it needs to fetch from the method store first. So that's something new. So based on that, you will know that we do the balance by implementing a load balancing provider. That's a special provider. So your application just need to register with this single provider register. And then you load the other providers into your application's context. And then in the load balancing provider, get the mirror of the real provider. Okay. The real provider. So in your application, it's about here. It's called the, combine the load balancing provider, and this provider will have the information of all the other providers you registered, you loaded. Okay, so with the strategy which is implemented by the load balancing provider, your application can go among all the child providers. So to find the best candidate for their job. Okay. So then we implemented we use the Java. You know, most of the applications in the big data world right now is in the written by Java. So there are Hadoop, HBase, and much more. So we need to export this capability, the load balancing capability, to the Java world. So our method is to implement another. They also call it provider in the Java world. Sorry about that. So people like this name, I guess. So the KE provider will in the Java, it will call the load balancing provider, and then load balancing provider will help the application to allocate to assign the tasks to either the hardware provider or the software provider. It's also easy to use. You just need to change one line in your JDK. Dition JDK is the version derived from the OpenJDK project, and it's open sourced by HiSilicon, Huawei. Okay. So here are some. Sorry about that. Okay. I just need 2 more minutes. Okay. Thank you. And here are some measurements. So we see with the load balancing feature, at the same CPU utilization, like the red one, we get higher bandwidths. So similarly, here, same CPU utilization, we get higher, and here is to get the same bandwidth we use with the balancing. We just need lower CPU utilization. So here is another demo we did on the HDFS Hadoop file system. So with our method, we can achieve about 30% performance gains. So with jobs assigned to both the hardware accelerator and the CPU software core. Software accelerator. Okay, yeah. As for open source software, we always welcomes your contributions. Here's our project. This project is incubating under the OpenEULA Big Data SIG. So welcome to log in, join the community to check the code, to find the way to utilize your hardware better. So again, I'm from Linaro. Okay, that's almost it. Linaro works on Arm software. Yeah, welcome to ping us. Yeah, for any service request. Thank you.